All right, once you go past that step of removing common factors, the next thing that you should check for is the following special factor forms. The first two you guys should have been exposed to already. The last one might be new to you. And there's three special factor forms that you need to be able to work with. The first two are just the reverse operations from what we did in the last section. Okay, so in the last section, if we took the sum and difference of terms being multiplied by each other, it can be expanded out into the difference of squares. Now we're just working in the reverse direction. If you know, or if you're given a polynomial that is the difference of two squares, you can expand it out, or I'm sorry, you can factor it out into the sum and difference of those terms that are being squared. So you just take the two terms that are being squared, take their sum and difference, and that product is your set of factors. Okay. So for instance, if you took a problem that looked like this, 4x squared minus 25. What you would do is, again, look to see, are there any common factors? No. Are your two terms each perfect squares? And so you'd need to check and see what base is being squared to give you this first term. 2x. And what base would you square to get your second term? 5. And so here it fits your pattern. The difference of squares can be factored into the sum and difference of those bases. So your bases are 2x and 5. So you simply take the sum and difference, and that becomes your set of factors. Okay, so knowing this pattern is probably quicker than trying to go through and solve it with your calculator, because it's a pretty basic pattern. And now I'll complicate things slightly by giving you a problem that resembles the following. Does this problem fit the same form? Is this the difference of two bases being squared? Yeah. Now, many of you are going to be tempted to expand out the first polynomial, combine all the like terms, so then you'd subtract 25 from that, and then you'd look to try to factor it again by hand, okay, which is what we'll talk about in the last section, so next week. But it might be easier for you to recognize this fits the pattern of difference of squares. This first term is already written as your exponential. It's a base squared minus, and what base can we square to get 25 again? 5. And so this fits the pattern, and the pattern is the sum and difference of these bases or terms. So if we take our two terms, 2x plus 1 and 5, and we take the sum of those and the difference of those, and now instead of having to simplify and factor more complex numbers, all we have to do is simplify these basic terms. We get 2x, 1 plus 5 is 6, and here we get 2x, 1 minus 5 is negative 4. And now, is this completed? Have we completely factored this? Okay, and here's another thing to keep in mind. This very first step of removing any common factors, you do have to go back and kind of recycle through that. If at any time your factors have any common factors, you have to remove them. So what do you notice about this first factor here? There's a common factor of 2 that you can remove, so you need to remove that factor of 2. What's that going to leave for your two terms? X plus 3. And then what about the second one? Also, you can remove a 2. And that leaves an x minus 2. And so your final answer for this, when you completely simplify, 2 times 2 is 4. X plus 3, x minus 2. So this would be your fully factored form for this answer. Anything that stops short of that is incomplete. And so be aware of that restriction. and check that. Recycle back through, making sure that there's no common factors left. All right, in addition to difference of squares, the other pattern that we looked at in the expansion of polynomials was a binomial square, and that expanded into the first term squared plus twice the product of those terms plus the second term squared. So if you recognize that, and it's called a perfect square trinomial form, if you recognize this form in a polynomial, it should cue you in that your factors will be a binomial square. Okay, once again, the signs here come into play. If this happened to be a negative, this would be a negative as well. You don't have to memorize two different equations or forms here, because the signs will take care of themselves if you just follow this form written in red. Okay, and let's say we take an example of this. So if you're looking to factor this expression, again, look for any common factors to remove. There are none. Look to see, are your first and last term both perfect squares? In this case, they are. So what base can you square to get this first term? Again, it's the same as the problem above. And then the 25, you square the base of 5. Okay, so the next test that you do to see if it fits this perfect square trinomial form is if you take the bases that are being squared on the first and last terms and you multiply them and then double that product, do you get this middle term? Is 2x times 5 equal to equal to the 20? Or 2x times 5 and then you double that, is it equal to 20? Yeah. So if you double this and it equals 20, then you have this perfect square trinomial form. And so right away you know your factors will be binomial square. The two terms are these bases that you squared at the first and last term. And the sign between it is whatever the sign is of your middle term. So in this case, that was a negative sign. And so your answer, the factored form of that expression, would be the 2x minus 5 quantity squared. All right, see if you can factor the following. Are your first and last terms perfect squares here? No, but is that the first step you should do when factoring? No, again, go back, look to see, are there any common factors you can remove? If you remove a 2 first, that leaves you with 4x squared plus 12x plus 9. Now, does it fit this pattern? Are your first and last terms each perfect squares? Yeah, the first term is 2x quantity squared. The last term is 3 squared. If you take the product of these two terms and double it, do you get this middle term? 2x times 3 is 6x. Double that, you get 12x. So yes. So when you factor, you leave your 2 out front. You're going to have a binomial square. The binomial will be formed with the terms of 2x and 3. And the sign that goes between these will be whatever the sign is of this middle term. So in this case, a plus. All right, questions regarding these two patterns? It's the difference of squares in a perfect square trinomial form. These are the ones that you should have had some exposure to. The last one, which will be new to you possibly, is binomial, or is the sum and difference of cubes. And so if you have two perfect cubes that are either added or subtracted from each other, they do have a special pattern for factoring. And that pattern is going to have two factors. The first factor is a binomial. It's just going to be the sum of the bases that are being cubed to get those numbers. And then your second factor is a trinomial. And that trinomial will have a first term of this base squared. Whatever base is being cubed, if you square that, the last term is going to be the second base squared. And then the middle term of this trinomial is going to be the opposite of the product of those two bases. So a times b, and then change the sign of it, and that gives you your pattern for those factors. Okay, so once again, if we take 64 minus 27x cubed as an example, you recognize to see first any common factors you can remove? None. So you look to see, are you dealing with the difference of two cubes? Is 64 a perfect cube? Yeah, it's the base 4 cubed. Is negative 27x cubed a perfect cube? Yeah, it's negative 3x quantity cubed. Here again you see that the negative sign is going to take care of itself here. You only need to memorize this one form even though you can find two different forms for it. But when you factor this sum or difference of cubes, you're just going to take the sum of the bases, so 4 plus a negative 3x. And then your second factor is going to be the first base squared, so 4 squared is 16. Your last base is going to be the second base squared, so negative 3x quantity squared is 9x squared. And then your middle term is simply going to be the opposite of this product. So 4 times a negative 3x is negative 12x. Change that sign, it becomes a positive 12x. And now, here is one potential form of the answer. Like I said before, it's very likely that all your factors will be written in standard form with leading coefficients of positive 1. So if that were the case, this factor right here would be 9x squared plus 12x plus 16. And this factor, because the leading coefficient needs to be or is often written positive, if we moved this term in front and changed it to a positive, the only way we can do that is to factor out a negative. And if we factored out a negative from each of these terms, we change the sign of each one. So the 4 becomes a negative 4 and a positive 3x. And so it's very likely, like if you entered this in your calculators, this is the form it would give you in your calculator so that it fit those restrictions. Okay. Now, what do you notice about the first and last term of this factor? 9x squared and 16. Are both of those perfect squares? Do you think it's going to fit that perfect square trinomial form? No, because if it did, we wouldn't have used this as a pattern, right? This factor cannot be simplified any further than it is right here. Otherwise, it would be simplified in the pattern that I'd ask you to remember. Okay. Many students mistakenly try to factor this. They maybe turn it into 3x plus 4 quantity squared, but it's not. That's not equivalent to that. It can't be factored any further. And so be very careful on those.